Okay, I'm going to go ahead and get started. It's 8:20. So start with announcements. So today is another quiz day, right? Quiz 2, same format, same rules as last Friday. It will become available at 9:30 this morning. Once you open it, you have 2 hours to upload your work. And all work must be submitted by no later than 11:59 p.m. today. Remember the rules, same rules. They're posted written at the beginning of the quiz so that you can be reminded. Don't forget, in addition to following the rules, you need to sign your name beside your written name. The signature is saying to me, I have followed the rules. Okay, so that is something to put in your calendar for today so that you don't forget. Set aside enough time today to do that. Beyond today, the next thing is the next set of Wiley Plus problems. That'll be due next Monday night. Okay. Please also turn in your lab reports soon. Okay. It takes me quite a long time to grade them, so I need to be getting them turned in. Okay. Don't forget that for the lab next week, we start experiment 3. So you need to read that experiment before you come in. And don't forget, starting with experiment 3, there is what's called a pre-lab, which is a question that's posed to you at the beginning in the lab manual of experiment 3. And you are to do a calculation based on that question and then send me your work. You can just email it to me before the lab begins. Okay. Okay, so those are the things that are coming up in the near future. Alex.
And the lab reports are due today?
They're due today. Okay, lab reports are due today. Okay, so let's pick up with this practice set of questions for two-dimensional kinematics. Let me remind you, I showed you this simulation on Wednesday. You're looking down from above on an XY coordinate system. You might imagine that it represents a flat surface like a field or a parking lot or something like that. And there's a particle moving around. I think I talked Wednesday to pretend it's a squirrel. Who cares what it is? The black curve is its actual path that it takes in the XY plane. The initial time has been chosen for us called T1. It's set at 2 seconds. That's where the squirrel is at that time, T1, right there. So that blue arrow we said was its initial position, R1. And we estimated that vector's components by just looking on the scales there, X and Y. Here's what we got for that position vector in what's called unit vector notation. 5 meter I hat plus 21 meter J hat. Okay. Then we took time T2, the quote unquote final time, just based on the slider here in the animation. Right now, T2 is set at 6 seconds. And there's the particle, the red dot, there's the squirrel at time T2. So there's the position vector from the origin out to where it is for time T2, that blue arrow. So that would be labeled R2, position vector at time T2. And again, we estimated the X and Y components just by looking on the scales here. We got R2 equals 21 meters I hat plus 5 meters J hat. Then I said, let's find the displacement of the squirrel between T1 and T2. Because the position has changed, right? From that vector to that vector. And change in position is displacement. And now we label displacement delta R arrow. And it just means R final minus R initial, but that's vector subtraction, where you have to deal with components. But it's not hard. You just take the difference in the X coordinates times I hat, plus the difference in the Y coordinates times J hat to get the displacement. So you just got to take x final minus x initial, 21 minus 5, you get 16 meters I hat. And for delta y, it takes y final minus y initial, 5 minus 21, negative 16 meters j hat. So the displacement has a positive x component and a negative y component. It points to the right and down. And that's the green arrow right there, the green open-tipped arrow, which points from the initial location to the final location. And you can see it points to the right and down. And I sketched its two scalar components. There's the x scalar component, delta x, and there's the y scalar component, delta y. Okay? All right, now that was just getting warmed up. Any questions about what we did there? Practicing with two-dimensional kinematics. Okay, I'm going to read to you what we're going to do next, okay? It will be part A, because this was just getting warmed up. A. What is the particle's displacement delta r between time t1, just set 2 seconds, and the instant it crosses the x-axis? And what is the magnitude of this displacement? Say it again. What is the displacement between t1 and the instant when it crosses the x-axis? Now, if you were doing this on Wiley Plus as an interactive exercise, you would have control of this animation and you would have control of that slider. So what would you do to figure out how to answer this question? Okay, now we already know where it is at T1, right? That's R1. So we know that. But we got to find when it crosses the x-axis, right? You want to add something? Right, and I think that's what Malachi is saying we should do. We take this slider and we move it until the particle is on the x-axis, right? Just get it roughly right. Okay. Wiley Plus gives us a 2% tolerance. So assuming we can move that slider carefully enough, right? There we are. Is it not on the x-axis? Happens to be at what time? Well, T2 looks like it's about 6.65 seconds. It doesn't ask us when that happens though, does it? It just asks us what's the displacement between T1 and that T2. We don't even have to calculate anything, do I? Isn't it displayed right there on the slide? There's the delta R, 19.36 meters I hat, so large and positive, and negative 20.87 meters J hat, so large and negative. And there's the positive delta X, and there's the negative delta Y, and there's the actual delta R arrow. Okay? How would I find the magnitude of that displacement? Yeah.
It's the positive or absolute value of whatever value you get.
So here's what I get. Delta R arrow equals 19.36 meters I hat plus negative 20.87 meters J hat. So how do I find that? Notice that's what that would be denoted. That's the magnitude.
You omit the direction of the sign.
Okay, so but what do I do with these two numbers? Just add? Pythagoras. So what do I do to the numbers? Square them, add them, and then take the square root, yes? 19.36 meters squared plus negative 20.87 meters squared. Of course, that negative sign on that component then doesn't matter. And then take the square root. I got 28.5 roughly to 3 sig figs. And that's the magnitude of the displacement. If you like, that's the length of the green open-tipped arrow. Okay? I'm sorry? I have a difficult time hearing. Yeah, the green open-tipped arrows. There's a lot of arrows, so it's the green one that starts there, goes down there, and there's its open tip right there where the squirrel is. Okay. Here's the next question. Is the magnitude of the particle's displacement for this time interval, in other words, that number right there, is that magnitude equal to the distance the squirrel traveled? For this time interval. I see some nodding and I hear a yes. Yeah, Nick. So the magnitude of the displacement is the length of that green arrow, but it actually traveled along that curved path, didn't it? Does that curved path lie directly along the green arrow? No, it's a little bit of curve there to it, isn't it? So the actual ground covered would be along the black part, which is going to be a little bit longer, I think, than the magnitude of the displacement. Point there is, the point to take away from that is, magnitude of displacement is not necessarily the same thing as distance traveled. Here's another question. What is the average velocity of the particle for the time interval from t1 equal to 2 seconds and t2 equal to 10 seconds? So what would I do with the animation? Gabrielle. Yeah, but we actually know when it starts. Oh, sorry. That's right. And then so you find over time. Okay, but I contend I have to do something with that slider up there in order to do what you just said, which is the correct thing to do. I have to move it up until T2 is at 10. It says 10, okay? So, turns out that's the maximum I can go. Puts it way down there, see it? That's where it is at T2 equals 10 seconds. So I am to find the average velocity for the squirrel for the interval that begins at T1 equals 2 seconds and ends at T2 equals 10. And you can see a lot of vectors there, yes? R1 is the same, there's the R2. There is the delta R. So how would I find V average? So part B, by the way, the answer was no. How do I find V AVG arrow? Yes. Yes, there will be X and Y components. How do I find those two things? Those two components. Sorry? Well, what I know is delta R. Is that what you're saying? I'm going to need that? That's delta R. Is that the answer? It's V. I want V average. I want the average velocity. Yeah. And do what? Which vectors are you referring to? Kylie? And what's the name for change in position? Displacement. Isn't that what this is? Definition of V average is displacement delta R arrow over time interval. That's its definition. So that's what you want to go to. Okay. Now the good news is the animation gives you the delta R arrow, right? And it's in unit vector notation, which is about the handiest notation there is, because you can read right off the X and Y components. Delta R arrow for this case is 40 meters I hat plus negative 56 meters J hat. There's the positive 40 meters. There's the negative 56. So what do I do? Or what do I have to do with that delta R? Got to divide each component by what number? 8. Yeah, watch out. Delta T is 10 minus 2, or 8. Okay? So you just take 40 meters I hat plus negative 56 meters J hat, and you divide both parts by delta T, which is 8 seconds. You got to divide both parts, both components. So what is that? Well, what's the X component of V average? I think that's 5, isn't it? Meters per second. I hat, that's 40 divided by 8. And then what's the next one? Isn't it negative 7 meters per second times J hat? Okay? This is just some practice with dealing with vectors in 2 dimensions, because the practice is helpful. Now I want to do a little bit of practice with vectors in 3 dimensions, because that gets even a little trickier, especially since to represent motion in 3 dimensions, we're only going to have 2 dimensions to work with to represent it. Yes. Well, if I had asked you for the magnitude of V average, you would have taken the square root of that number squared plus that number squared. Well, there's a vector, and then there's the magnitude part of a vector. A vector has 2 parts, a magnitude and a direction. This is the full vector. Sometimes we'll ask for the full vector. Sometimes we'll ask just for the magnitude part, because maybe we're only interested in how big the vector is and not what direction it's pointing in. All right, so we've got an entity that has multiple parts, a magnitude and a direction. And sometimes we might ask you for all the parts, and sometimes we might ask you only for one of the parts. Okay. Does somebody else have a question? I thought somebody did. No? Okay, so let's go now to this. Let's practice with kinematics in 3 dimensions, all right? I'm gonna need a little bit of room here. Again, what I'm saying now is that we are burdened with the situation of representing 3-dimensional motion on a 2-dimensional surface. And it can get a little bit tricky until you get used to it, okay? So this is just a little bit of practice with kinematics in 3-dimensional motion. I'll give you the scenario, then we'll talk about the picture. The figure below shows the initial position I, there it is, and the final position F of a vampire bat that's flying through the air at night relative to an X, Y, Z coordinate system. 3 dimensions now, X and Y and Z. And they're going to try to represent that initial and final position by trying to represent the full 3-dimensional coordinate system. They have chosen to draw an X-axis going to the right in the plane of the screen, the Y-axis going upward in the plane of the screen, and the way they've drawn this line, and see how they labeled it Z? All of the axes have to be perpendicular to each other, so that Z-axis technically is coming straight out of the screen towards you. But you can't draw that on the screen, so you draw it slanted like that. It's what I call a perspective view. Okay? Question? Well, you will have 3 axes, 2 in the plane of the board and 1 coming out. How you label them is up to you, as long as it's what's called a right-handed coordinate system. So if that's X, that's Y, that's Z. Okay? If that's X, then that's Y, you can choose, then that's Z. That's also acceptable, but you are going to be working in some of these problems with 3D. So you will have 3 axes. All right, here's the first question. What is the initial position vector? R initial arrow in unit vector notation. It's trying to convey where the initial point is, yes? We need to be able to, using these numbers that you see, write down the X component of R initial times I hat, plus the Y component times J hat, plus the Z component times, that unit vector for the Z axis is called K hat. This is just where it is. What is its X coordinate? This first number. Look at the picture carefully. What is the bat's X coordinate if that's where it's located? Adrian. 7. We're just kind of breaking it up into parts, yes? You always start at the origin. That's where the axes cross. You go 4 meters out along X. This is not along X, so it doesn't count. This is not along X, so it doesn't count. Now you're back along X again, going 3 more meters. So 7 meters I hat. Okay. All right. What's the Y coordinate of the bat? Let's look carefully. Again, you got to try to visualize 3D here. Oh, are you saying the answer? Yeah. 1 meter, because there's how far you go parallel to Y right there, yes? So 1 meter, J hat. So what's the Z coordinate? Let's look carefully there. Thoughts? What you think, Kylie? Z is positive towards you. Excellent. -2 meters, because it's going back that way, isn't it? Parallel to the Z. How far? 2 meters, but back. Because plus Z is coming out at you, and you have to go back 2 meters. Okay? Let's practice some more. What's the final position vector? RF arrow. Take a minute and try it for yourself. Write it on your paper. Okay? Let's see what you got. For our final, what's the X coordinate? Yeah, Drew. There we go. Yeah, you really got to concentrate, don't you? See, wait a minute, which direction am I talking about? Oh, X. Okay, how far? You always start at the origin, but where's the X motion? There it is. 5 meters in the positive direction. So 5 meters I hat. What's the Y coordinate? Yes. -3 meters. J hat then. What's Z? A little tricky. Say again? 1 meter, right? Because you first go out in the positive direction of Z 4 meters, that doesn't count, but then you backtrack in the negative z direction by 3 meters. So the net effect is positive 1 meter k hat. Okay? What's the displacement vector, delta r, for the bat between the initial point and the final point? Why don't you try that? Calculate that, see what you get. Delta r arrow. Your job is to fill in those 3 numbers in those parentheses. Question? Delta r, of course, means change in position. So we're talking about between the initial and the final, right? One bat flittering around in the air at night. Okay, what did you get here? This would be delta x. Drew? Right? X final minus X initial. That's what delta X means. Negative 2 meters. The X component of the displacement is negative. Okay, what's delta Y? Good. Negative 4 meters. And so what's delta Z? Three meters. Positive 3. X component of the displacement's negative, the Y component's negative, but the Z component is positive. Try to visualize. If I asked you to draw delta R arrow on this picture, what would you draw? Or sketch, if you prefer. If I asked you to sketch delta R arrow on this picture, what would you draw? Yeah. So you draw an arrow. The arrow would start here and just point directly to here. Yes? With the tip there, not the other way around. From initial to final. Could you calculate the magnitude of delta R if I asked you? Good. You know how to extend Pythagoras to 3D? Just add on another plus Z component squared. All right? So if I asked you to find the magnitude of this delta R, you would take the square root of negative 2 meters squared plus negative 4 meters squared plus 3 meters squared. Square root, right? Okay, that's all you do. Just tack on the Z part squared. Would that magnitude of the displacement equal the distance the bat flew from I to F? Here I contend you need a little common sense. Can you picture how bats fly? Is the magnitude of the bat's displacement from I to F equal, you think, to the distance the bat flew? No, probably not even close, because bats flitter and go all in convoluted ways, right? From one point to another. And however that total distance that would be the distance it flew, that's probably going to be a lot more than whatever this magnitude turns out to be. One more. Suppose the bat flies from the point I, position I, to position F in a time interval delta T of 10 seconds. What is the average velocity, VAVG, in unit vector notation? What is VAVG? Just tell me what you would do, okay? How would you calculate this? Divide the delta R vector by delta T. And the delta T is 10. So take each one of these delta R components and divide it by 10, right? Bingo. Bob's your uncle, as they say in England. Negative 0.2 meters per second I hat plus negative 0.4 meters per second J hat plus 0.3 meters per second K hat. Okay? It's not hard once you say, okay, I'm starting to see what they're asking here. All right. Now, I'm going to transition to projectile motion, the topic of today's video lecture. Okay? All right, now, you can see, don't forget, of course, you had 2 videos for yesterday to watch. You had a video lecture for Thursday and then a class video. So those have presumably you've already watched. And then you had the video lecture for today, which was on projectile motion. Okay. So there are the learning objectives from section 4.4 in your book. Those are all the things that we need to be able to do. I'm going to let you read those for yourselves while I frame what we're going to do next with a few questions kind of back and forth that I want us to do. First thing, I want us to be very clear on what we means the world of professional physicists, mean when we say projectile motion, so that you don't interpret something else. Okay? In projectile motion, some particle has been projected, which is just a way to say given an initial velocity. And there are a lot of ways you could give a particle an initial velocity. If this is a particle, I could throw it, right? Throwing is a way to project. If it's a soccer ball, I could kick it, right? If it's a golf ball, I could hit it with a club. Or a baseball, I could hit it with a bat. Or a cricket ball, I could hit it with a, what's it called? A bat, okay, right? Or whatever the cricket ball is called. Okay? Lots of ways you can get the particle projected, i.e. on all that means in this case for a physicist is somehow, some way, someone gives it an initial velocity. The projectile motion is only after the projecting is done. So you're not worried about the actual throwing of something. You understand what I'm saying? The projectile motion begins, let's say you're throwing something, the instant you let go. Because all you did was give it its initial velocity. And all I want to know is what was that initial velocity. I don't care about how you had to move your arm and how hard you moved it. And all. I don't care. It has nothing to do with projectile motion. Just get the thing moving. Because the projectile motion begins with the initial velocity. The instant whatever was touching it has let go. And therefore, the only influence in projectile motion is gravity. That's it. Nothing else can be touching or pushing or pulling on the object. Just gravity. Therefore, when the thing lands or hits something at the other end, that collision down there is not part of the projectile motion. Okay? We're not worried about that now. We're worried about that stuff later. The projectile motion is only the part where it's moving under the influence of gravity alone. So don't worry about the throwing or the projecting process, and don't worry about what happens when it hits something at the other end. Question here. No, you just have to be clear whether air resistance is to be included. In this class, the answer is no. No air resistance. You want to figure out how to include that? You take Physics 310, classical mechanics. Okay? So no, do not worry about air resistance. All right, now, the way our video lecture and our book sets this up, projectile motion is how many dimensions, right? If I throw this straight across the room, how many dimensions are we talking about? 2, right? the horizontal direction and the vertical direction. What's the horizontal axis called in the book? X. What's the vertical axis called? Y. Vertically up for plus y. In the horizontal motion, what kinematic quantities are constant? Can you list one or two for me? In the horizontal motion, in projectile motion, what kinematic quantities are constant? Adrian. Velocity. V sub x. Got to deal with components, right? Anything else constant? Sure. A sub x is constant. What is the value it happens to have? 0. But it's still 0 all the time. So you could say acceleration. In the vertical motion, what kinematic quantities are constant? Acceleration. A sub y. How would your book express A sub y in projectile motion? A sub y equals what?
Minus G.
Minus G. Salim said it. Minus G. Right? Is V sub y constant? The y velocity? No. Good. Don't fall for that. Okay? All right. So that's just warm up. Let's start practicing. So we're going to do a simulation for our international students. We're going to do a simulation where somebody hits a baseball with a bat. I don't really care about how the baseball gets moving. It has an initial velocity. Here's an XY coordinate system. X is along the ground and it's horizontal. Y is vertically up. You got a whole bunch of sliders here. Time for running the animation. You can pick Y initial, V initial X component, V initial Y component. Let's keep all those things where they are. Y initial is 1 meter, V initial X is 20 meters per second, V initial Y is 20 meters per second, okay? And you can run the animation and see it move. See lots of vectors there, okay? I showed you this also in the video lecture, okay? You can find all these animations on Wiley Plus. They're in Read Study Practice. So you can play around with it if you want to make sure you understand what all the vectors are. Here's the first question. Okay, let's get ourselves some space. Now we're practicing with projectile motion. And I'm going to ask some questions based on that animation. First question. What is the baseball's velocity in unit vector notation at its highest point? I want V arrow at its highest point. And I'll even set it up in a template for you. I want some number times I hat plus some number times J hat. You got all this information in front of you. Now,
Going to be A 10 times I hat plus 0 times J hat.
okay. Malachi is telling me, and Salim is also saying, that you take for the X, the initial value, 20 meters per second, and for the Y, 0, right? Because at the highest point, which is roughly there, right? The velocity has only an X component. Watch out for this question. The most common mistake is to answer this question too fast and say the velocity at the highest point is 0. You see why that's not a correct answer? Because first of all, we're in 2 dimensions, so we have 2 components. One of those components is 0 at the highest point, the Y component. But the X component of the velocity can't change, right? And if the X velocity was initially 20 meters per second, then it's still 20 meters per second at the highest point. Okay, all right, let's do another one. What is the baseball's acceleration in unit vector notation at its highest point? A, arrow. Here, why don't we just do symbols? Let's just do symbols. What do you think about that, Gabrielle? All right, so to show you the shorthand way the physicist would write that, they would just write that. Negative G, J hat. Meaning there is no X component, right? And the Y component of the acceleration is negative G. Magnitude G, negative means directed down. Right? Question.
So in this case, because the acceleration, the extraction was zero, we just forgot writing it. But we do the same with part A.
Yes. Yes, you can. You could write the answer to part A, V equals 20 meters per second, I hat, stop. Okay. All right, here's another one. C, what is the maximum height reached? Here's what I want. We'll estimate from the animation and we'll calculate to 3 significant figures. I'm going to call the maximum height H. Can you see how to estimate it from the animation? I tried to get it roughly. Just try to get it there at the highest point, close as you can. The word height implies what coordinate? Y. So what's your estimate of Y? Yeah, it's about 21, 22. Yeah, yeah, it's just a little more than 20 meters, right? Now, that's fine. That's a good estimate from the animation. It gives us a sense of how high. Let's calculate it using the physics I talked about in the lecture for today. All right, let's calculate that. What special kind of equations do we get to use here? Constant acceleration equations. Should I use them for X or Y? Because they apply to both. I think Y here, right? Because we want, H is a Y coordinate, isn't it? It's asking for a Y value, isn't it? Okay, but now I always think of the constant acceleration equations as coming in 3. There are 3 of them. V equals V initial plus AT, and so forth. Delta Y equals V initial T plus 1/2 AT squared. V squared equals V initial squared plus 2A delta Y, where all vectors are Y components. Which one do you want to try to use to find the maximum height? You have an idea, Malachi? Okay, and I'm even going to add, like I emphasized in my lecture, the little subscripts to denote components, right? The third one, yes? Why? Because I don't want to know the time at the highest point, right? I don't want an equation with t in it if all I want is the maximum height. I agree. Let's start with this. But now let's figure out what are the actual details here. How do I actually use this correctly, everybody? Watch out for that. You'll see what I mean in a minute. Use this correctly to find H. Thought here? Ah, that's an important point. If we're at the highest point, that Vy value is 0, isn't it? So you put a 0 on the left. Now here's V initial Y. I'm not worried about that. You see why I'm not worried about that? I know what it is, don't I? Plus 2 times, now for the AY, put in the expression negative G, yes? Negative G. What do I put for the delta Y? you know what to put for the delta y? But I want to use a symbol. You're right, I don't know a number, but notice what I said I want to call it something. 8, isn't that what the delta y is? Y final and y initial was, oh. What's the y initial? It's 1, isn't it? Oh, so actually, it's h minus 1, isn't it? You have a question? No. First of all, when you substitute g, you put in 9.8. But we will do that, yes. Okay. All right. Shall we see how to solve this? Well, take that over. Negative v initial y squared equals negative 2g times h minus 1 meter. Ah, I have a negative on both sides, don't I? They cancel, so don't care about the negatives. Divide both sides by 2g. So v initial y squared over 2g equals h minus 1 meter. Add 1 meter to both sides. And that should be how I can get h. For the v initial y, you put in 20 meters per second, right? Don't forget to square it though. 20 meters per second squared divided by 2. Now for the g, you can indeed put in, but note how I write it, 9.80 meters per second squared. Okay? And then add 1 meter to it. So I get 21.4 meters. Pretty good, right? Compared to our estimate. See what I'm saying? The estimate was just to give us a sanity check when we did the calculation. All right, here's another part. What's the horizontal distance traveled from the starting point to the landing point? So let me slide the time slider because it goes all the way to where it lands. Do you see? So my question is, what's the horizontal distance traveled from where it started to where it ended? I'm going to call that, notice how I'm going to denote it, delta x. How much did its x change by? Thought on how to calculate that? You can estimate it, can't you? First, you want to try that first, so we have a sanity check? Isn't it just a matter of estimating off the x-axis? It started at the origin, didn't it, for x? Started at the origin for x. Where do you think it lands? Looks like it's a little past 80 meters, right? But how are we going to calculate it?
Since the horizontal axis is constant, you're going to be using the horizontal velocity.
Boom. It's just constant acceleration equation number 2 for x. Delta x equals v initial x t plus 1/2 ax t squared, but substitute what the ax is. 0. Okay. Now you get to use information on the screen, so what would you do now to finish this? To plug in numbers. What numbers do you plug in? Here and here. What do you plug for v initial x? 20 meters per second. What do you plug in for t? 4.12 seconds. you get 82.5 meters, which satisfies the sanity check because we said it looks like it's a little more than 80. All right, two more quick things I want to do with this. One of the things I mentioned in the video lecture for today was this special equation called the range equation, which is very handy in projectile motion if what you want to find is the horizontal distance between firing and landing, if the firing and the landing are at the same y value. Then you can use that special equation for what they call R, the range. Could I use the range equation in this scenario? Aha!
No, sadly.
No, correct. People are telling me no, because the initial y, 1 meter, is not the same as the final y. I will tell you what the range equation gives. It gives 81.6 meters, a little less than the correct answer, yes? Because the starting point and the ending point y's are not that much different. Understand what I'm saying? But be careful, technically the range equation is going to give you an inaccurate answer. However, what the range equation gives you for the horizontal distance is probably within 2% of that correct answer. So guess what? If you use the range equation and put it into Wiley plus, what would Wiley plus say? Okay. If you did that on a test, what would I say? No. Okay. One more thing, and then we'll stop for today. I want to show you a little video that we made yesterday. Get to it. Of a little particle traveling on a cart. And what happens in this video is the little cart's going to come along on this track, traveling at a constant horizontal velocity. And when it passes this little post, it shoots a ball vertically up relative to it. And it keeps rolling. So the ball is going to do projectile motion. As the cart rolls and the ball goes through projectile motion, the question is, where will the ball land? Will it land in the cart? Will it land behind the cart? Or will it land in front of the cart? You understand what I'm saying? Let you think about that for just a second. Understand the scenarios? Then we're just going to play the video so you can see it. Everybody just go ahead and get a thought in your mind. You don't have to say anything, but it's good to make a guess. And then we'll show the video. It's going to be coming from over here. It's in slow motion. There it comes. Fire the ball. It lands right in the cart again. So you might want to think about that a little bit. Something to think about over the weekend when you're bored. Can you explain why it lands back in the cart? Okay. If you want to try another challenge, do the whole thing again with this end tilted up so that it slides down like a ramp and shoots the ball. Will it land in the cup again, or will it miss? Okay. Okay. Don't forget to do the quiz today. And don't forget to turn in your lab reports, and then have a good weekend.
Thank you.
You're welcome. You're welcome. Yes. Sorry. I didn't.
I cannot.
No, I did. Thank you. Phew, you scared me for a minute, but it's a good question. I did remember. It's okay, and it's all right. I don't know, maybe you should have a special signal or something. Maybe you should just point to the phone and that's your way of asking me.
Got it.
And all I have to do is say this or, oh, yeah. But thank you for asking.